We are moving on to section 5-6, or radical expressions. We're going to start by simplifying these following radicals as a warm-up. We have the cube root of m to the 6th, n to the 10th. In order to simplify, we have the cube root of m to the 6th, and then we break down our n to the 10th so that we have n to the 9th and n to the 1st power. That way our n to the 9th is divisible by 3, giving us m squared, n cubed, and then the cubed root of n. Next one, we have a square root. So our square root of 16 gives us 4. The square root of a to the 10th is a to the 5th, but remember, it must go inside our absolute value bars because it's the even power divided by an even root gives you an odd exponent rule. And lastly, b to the 8th divided by 2 is b to the 4th. Then we have the cube root of the quantity 5a squared b to the 6th power. When you simplify this, you're just dividing the entire quantity of 6 by 3, so we get 5a squared b to the 2nd power. We then can simplify that to get 25a to the 4th b squared. Moving on from there, we're going to talk about the product property of radicals. With our product property, what it's saying is that if you have a common root, you can multiply the two numbers underneath that radicand so that you can have that common root with your terms together. Or you could separate it. You could take your two terms from outside or from inside the radicand and put them underneath separate radicals. The quotient property, here you can take a fraction and either put it together underneath one radical or separate your fraction into numerator and denominator in order to simplify. Simplifying a square root. Factor the radicand into as many squares or even powers as possible. Use the product property to isolate perfect squares, and then simplify each radical. So for example, we're going to simplify the square root of 25a to the 4th b to the 9th. So in order to do that, we need to make sure that our exponents are divisible by 2. So here, if we look at this, we've got 25, which is a perfect square. We have a to the 4th. 4 is divisible by 2. And then we want to again separate our b's into b to the 8th and b to the 1st. Then a to the 4th and b to the 8th are both divisible by 2. So when I simplify this, I get 5a squared b to the 4th, and then we have our square root of b left over as part of the answer. Moving on, next example, we're going to simplify the square root of 24a cubed b to the 2nd. 24 is not a perfect square, so I need to separate it into my two factors, 4 and 6, because 4 is the largest perfect square factor of 24. I then have a squared times a and b squared. Now I can simplify this. A 2 comes out, an a comes out, and a b comes out. I do have to put the b inside absolute value bars because it's the even, odd rule. Now, you may say, why is the a not in absolute value bars? It's because the original problem had an odd exponent. So only if the original problem has an even root and an even exponent does the rule apply. I still then am left with the square root of 6a. So 2a absolute value of b times the square root of 6a. Simplifying nth roots, we're going to find factors that are nth powers or easily divisible by n and use the product property. So if I have a cubed root, first of all, I need to find a perfect cube factor of 40. So doing that, I'm going to simplify 40 into 8 times 5 because 8 is a perfect cube factor. Then I want my exponents on my variables to also be divisible by 3. So x cubed works. I need to separate y to the 5th into y cubed times y squared. When I simplify this now, I take the cubed root of 8, which is 2, the cubed root of x cubed, which is x, the cubed root of y cubed, which is y, and I'm left with the cubed root of 5y squared. A radical expression in its simplest form. First, the index n is as small as possible. For the index n, the radicand contains no factors other than 1 that are perfect squares or that are nth powers or an integer or polynomial. The radicand contains no fractions. No radicals appear in the denominator. When the denominator contains a radical, rationalize the denominator, which means multiply the numerator and the denominator by a radical that will make the denominator an exact root. Then you simplify. For example, I have 5 over 2 times the square root of 3. I cannot leave that radical in the denominator, so I'm going to multiply by square root of 3 over square root of 3. That brings my square root into the numerator, so 5 square root of 3. In the denominator, I now have 2 times the square root of 9, which comes out as just a 3. So it technically is just 2 times 3 in the denominator. So 5 square root of 3 over 6. Next one is a quotient inside my radicand, so I can separate that out. The square root of y to the 8th over the square root of x to the 7th, which I want to separate into x to the 6th times x. I then can simplify this as well. So I have y to the 4th, and here I have x cubed, and then square root of x. Now I cannot leave that square root of x in the denominator, so what I'm going to do is multiply by the square root of x over the square root of x. When I do that, I'm left with y to the 4th square root of x over x to the 4th. Now the next one is similar. When I simplify the next one, I now have a cubed root. So I have the cubed root of 2 over the cubed root of 3t. Well, if I think about this, if I multiply by 3t, I'm only going to get 9t squared. So I want to turn 3t into a perfect cube. In order to do that, I need to multiply by the cubed root of 9t squared. Watch what happens when I multiply by the cubed root of 9t squared. By doing that, I now have the cubed root of 18t squared in the numerator, which we aren't really concerned about. But in the denominator, I have the cubed root of 27t cubed. 27 and t cubed are both perfect cubes. So they all cancel out, and I'm left with 3t in the denominator. So my answer is the cubed root of 18t squared over 3t. Simplifying the next one, if I look at this one as well, I'm dealing with perfect cubes. So I'm going to simplify, so I have the cube root of 2 in the numerator and the cube root of 16x. Now here, I want to turn 16x into a perfect cube as well. So in order to do that, I want to multiply by the cube root of 4x squared. Cube root of 4x squared in the numerator as well. So now in the numerator, I have the cube root of 8x. In my denominator, the cube root of 64x cubed. 64 and x cubed are all perfect cubes. So, cube root of 8 comes out as a 2. Cube root of x is left. In the denominator, a 4x comes out. Last thing I have to look at is simplifying what's on the outside of my radical, which is the 2 and the 4 can reduce to 1/2. So I'm left with the cubed root of x over 2x. Oops, and I'm sorry, I dropped my x squared somewhere in here. This should be a squared, this should be a squared, that should be a squared. Much better. Last example. Multiplying two cubed roots together, and then we're going to simplify them. You're going to multiply what's on the outside together. So 6 times 3 gives us 18. If we look at the inside, I've got n, 9n squared, and 24n. Well, we know n squared and n is going to work out well because that's going to give us n cubed. But if I multiply 9 times 24, it's going to give me a very big number, which then I have to find a factor of that is a perfect cube. Instead of doing that, I'm just going to rewrite this as 9 is 3 times 3. I'm going to keep my n squared. 24 is 3 times 8, and then an n. I have 3 3's. 3 times 3 times 3, I know, is 27. I also have 8. 27 and 8 are both perfect cubes. So, I have 18 already on the outside. I'm going to cross off my 3's and bring out one of them. I'm going to cross off my 8 and bring out a 2, because the cube root of 27 is 3 and the cube root of 8 is 2. I then also have 3 n's on the inside, so the cube root of n cubed comes out as an n. Now I just have to simplify this. 18 times 3 times 2 is 108 n. And I've easily simplified that without using a calculator.